Okay, so we're going to continue talking about our sort of overview of pharmacology. Previously, we were talking about a branch of pharmacology called pharmacokinetics. So pharmacokinetics and pharmacodynamics are sort of the different areas of pharmacology that we like to talk about. Pharmacokinetics, the big thing was ADME, absorption, distribution, metabolism, and excretion. We talked about each of those things a bit. We'll still talk about metabolism a little more in depth pretty soon. We also talked about clinical pharmacology, which is kind of like the broader sense of pharmacology, and trying to cure a disease clinically and all of the different stages of pharmacology that you need to address. Okay, so the next thing we're going to talk about is a related field. A related field called toxicology. Toxicology. So toxicology is kind of like pharmacology, it's just it deals with toxic substances. And we like to say that toxicology is like the opposite of pharmacology. The opposite of pharmacology, dealing with the adverse effects of different substances. Adverse effects of different substances. The interesting thing about toxicology is it's very complementary to pharmacology. Complementary. And a lot of the different processes that we study in pharmacology apply to toxicology. So things like metabolism, all the ADME processes, distribution, excretion, metabolism, also like the binding mechanisms, so mechanisms of drugs. All those things kind of apply to toxicology as well. And you can actually you can get a career in toxicology. You can be a scientific toxicologist as a career, and it's actually a lucrative career, and kind of it goes in hand with pharmacology, and there's a lot of interesting things to study that relate to toxicology. So let's show a couple toxic substances now. We've showed some therapeutically relevant substances. Let's talk about toxicity a bit. Okay? So, first one. A simple example is dimethyl sulfate. Dimethyl sulfate does not look that crazy as a molecule, but these things are toxic. What's toxic about it? Well, it's an alkylating agent. Alkylating agent. Does that make it a nucleophile or an electrophile? Well, things that alkylate, other things are usually electrophilic, so this is an electrophile. We actually know some of the electronics. This is delta minus, this is delta plus, delta minus, delta plus. And DNA, without drawing an actual piece of DNA, but DNA is nucleophilic. So this is an electrophile, this is a nucleophile. You can imagine that DNA would attack the methyl group and kick off this other part as a leaving group. And what do you get then? You get a DNA with a methyl group on it. And you certainly don't want to covalently modify your DNA. Usually that's not a good thing. And so this can lead to mutagenesis. So mutation of your DNA. That doesn't necessarily give you cancer, but it often does. And you can get cancer that way. So the study of how this all happens and if mutations are correctable in your body or not, that's another story. And But toxicologists deal with a lot of these kind of toxic substances and then see kind of, well, how are they toxic? How might dimethyl sulfate, which is actually a carcinogen, what's the mechanism of carcinogenesis, okay? All right, so that's one example. Let's see some more examples. And all right. Another example is something called benzo A, in brackets, benzo A pyrene. Benzo A pyrene. So this is a pretty intense carcinogen. And it's a something called a PAH. What's a PAH? It's a polycyclic aromatic hydrocarbon. Polycyclic aromatic hydrocarbon. All right, so what is the molecule and how is it carcinogenic? This is one of these molecules that has a couple benzene rings fused. So these are all benzene rings. And let's draw the double bonds. Double bond, double bond, double bond, double bond, double bond, double bond, double bond. Actually, we got to do this. Erase that one. So get to this point. So you have 3 double bonds, 2 double bonds, double bond up there. Double bond, double bond, double bond. And a double bond. Okay. You can also look up the structure of this. All right. Okay, so we talked about metabolic activation briefly, and some molecules are oxidized by enzymes like P450, right? So P450 is one of these enzymes. It's a liver metabolic enzyme, and it oxidizes things, and it definitely oxidizes this molecule. This stuff is found in tobacco smoke. And it's found in some charbroiled foods. It's found in a lot of things that you might encounter day to day. And it's a little scary because it is a carcinogen. Not directly, but after it gets metabolized. So what happens when it metabolizes, I'm going to erase this stuff up here. Okay, so what happens is we're going to it's a 2-step process where it epoxidizes one of the double bonds, and then it hydrolyzes the epoxide. Oxidizes and hydrolyzes, and you end up with a dialcohol. Alcohol, alcohol. Right there, everything else is the same. Oops. I drew it wrong. Okay, sorry, there's an extra ring. All right, so let's keep drawing it. Benzene, and we have all these benzenes with the alkenes. All right, we have that. The only effect was that you made a dialcohol, and that might not seem like it's that big of a deal, okay? However, then it does it again. Then it does it again. And so now it's going to epoxidize this top one that I've kind of indicated. So let's draw it again, but now make it an epoxide. Good to start with that. So that's 5 rings, right? 5 rings like that. Then we're going to fill this stuff in. Benzene, alkene, 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 alkene. Okay, so we filled in all the alkenes. But now, what I messed up here is that this is now an epoxide. So now you have an epoxide. And epoxides are also electrophilic. They like to be attacked by stuff. So of course it's delta negative. This is delta positive. The carbon. The carbon's delta positive, right? What do you think DNA is going to do to this stuff? Well, DNA being nucleophilic, we'll just attack right here. Attacks the carbon, and where do the electrons go? Onto the oxygen. So now you have DNA attached to this crazy molecule. And so we can draw that out. Again, start with three rings. There's the 4th ring. Now we have the 5th ring. Okay, so now DNA is right here. Right? And then we have hydroxy, 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 hydroxy. So we have some hydroxys, we have the DNA. And now we just throw in those double bonds. Double bond, 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 double bond. And now your DNA is alkylated. And it's the same exact problem, but maybe a little more severely. This now causes mutagenesis. Mutagenesis. And cancer. Sometimes your body has these kind of corrective mechanisms to unalkylate your DNA. And sometimes that works, sometimes it doesn't. But this stuff is pretty well known to be a carcinogen. And maybe the correction mechanisms don't work as well when you have benzopyrene attached to your DNA. Okay, so all right, so that's that. Oh yeah, this is actually there's a little bit of historical interest here. I'll draw it up here. Erase this. Okay, so there's a little bit of historical interest. This was discovered early in science. This was discovered in the 1700s. This was discovered, not all of the details of the toxicology, but there was a disease called chimney sweeper's carcinoma. Chimney sweeper's carcinoma, which is observed in 1775. So this wasn't just yesterday. This disease was the first reported occupational cancer. First reported occupational cancer. So early on, it was like a scrotum cancer, very dangerous, and it was due to chimney sweepers that are exposing their bodies to char, inside a chimney, and containing this chemical, and then it caused this cancer. Okay, so what was the overall thing? Was benzopyrene was oxidized once. It actually made an epoxide, and then it hydrolyzed it, so water got added, and that gave you the 2 alcohols. Then it epoxidized again, and now this is actually an active electrophile. DNA attacks this. Now you have this stuff attached to your DNA, and that causes mutagenesis and cancer. So, all right. Let's see what else about this. One more thing. I'm going to erase a little bit from the top, so make sure you got this. You can pause the video. Okay, I'm going to erase the occupational hazard. The other interesting thing in terms of toxicology is this area of the molecule is called the Bay region. Why is it called the Bay region? Well, it looks like a bay, kind of like Monterey Bay or something. And this is where a lot of the epoxidation happens, and kind of this region, and specifically that position gets epoxidized. And this is the position that really is known to cause the carcinogenicity of this. So if you hear people talk about benzopyrene, you may hear them talk about the Bay region. Okay, cool. So, all right, let's erase this. Okay, one more interesting thing about benzopyrene that is and kind of just toxicity of substances in general is that, let's draw this one more time. So you got your 5 benzenes. And we're just going to go straight to the epoxide. Okay. And your body does actually have a defense mechanism against your DNA just attacking this, or because your body is very it's trying to be resilient. It doesn't want to be your DNA just get destroyed anytime there's an electrophile in your body. So there is a reaction I should mention using something called glutathione. Glutathione. And glutathione is sort of like we call it a nucleophilic scavenger. A nucleophilic scavenger, so like a nucleophile that's in your body that's supposed to destroy stuff like this, because this is so detrimental to you. And what is glutathione? So glutathione is a small peptide. Okay, so that's like the initial part of the peptide. Oops. Okay, and then you have glycine. Let's see if it all came out. So what we have is sort of, we have carboxylic acid, then we have an amine, 2 carbons, C double bond O, NH, carbon, and then you have this other carbon up here. There's a carbon up top connected to an SH. And then it comes down and it continues the peptide. And so this is kind of like a glutamic acid, like a glue linked into the terminal carboxylic acid. So this is like a glue, glutamic acid. What's the amino acid that has a sulfur in it? It's cysteine. And then this is a glycine. So you can Google that structure also, glutathione. And anyway, what you should know, one of the things you should know about sulfur is that sulfur is nucleophilic. And so sulfur would actually attack this. Instead of DNA, that would be the hope, so that this gets destroyed and then excreted from your body. So this is almost like a phase 2 metabolism type thing, where you're taking this toxic metabolite and attaching glutathione to be attached to it. Let's draw what that looks like. We'll draw a abbreviated structure. And glutathione is also called GSH. GSH, that's like an abbreviation. GSH, what's GSH? It's glutathione. The thiol is the nucleophilic part. It's GSH. Anyway, so you could draw the product. Looks like that. So you get the five rings. And then this is like, it was GSH, we could call this GS now. GS is like everything with that sulfur thing attached. You got hydroxy, hydroxy. So you got some hydroxys. You have GS, which is referring to the whole part, glutathione attached. And fill in your double bonds. I think I did that right. Yeah, that's right. Now this can be safely excreted. The goal of glutathione, as a nucleophilic scavenger is to destroy electrophiles and have them safely be excreted. Okay? I should also mention there is an enzyme. This isn't all just magically happening with glutathione. There's an enzyme called GST. That's an enzyme, GST. So GST is being used. What is GST? It's called glutathione S transferase. Glutathione S transferase. What that's doing is it's transferring stuff onto the sulfur. So glutathione S transferase. Now, given that your genetic information in your body is so important, and this enzyme and this process is so important, do you think GST is a dominant or notable protein in your body? I mean, would that make sense? The GST that's used to kind of save your DNA from being destroyed. Would that be a abundant protein, or maybe something there's not very much of? Well, it turns out there's tons of it. There's tons of it. It's 10% of the soluble protein in your cell. There's tons of GST. So 10% of soluble protein. Is GST. So GST is very, very prevalent. Okay? That would make sense. All right. So this is glutathione, and how glutathione is kind of like a scavenger system that saves your DNA from what we might call an electrophilic insult. This is an electrophilic insult that might give you cancer. Okay? Okay, a couple more toxic substances before we continue on with therapeutic substances. So another example is benzene. Simple benzene, which is a organic solvent that we use to dissolve stuff in the lab. Doesn't look that crazy, but aromatic compounds do this sort of epoxidation and DNA alkylation thing. So this is also oxidized by P450. And then hydrolyzed. I think the enzyme that hydrolyzes the epoxide is called epoxide hydrolase. I may have misspelled it, hydrolase or hydrolase. But anyway, then it does it again. And it epoxidizes Another double bond. And now your DNA comes in. And now you have your toxic electrophilic metabolite. So now DNA would attach to one of these sides. And give like an alcohol, like that. And that is what would give you a cancer or something like that. That's benzene. What about, let's sneak it in over here. What about, and so when you're like, I mean, is this a big deal for us? Because, I mean, do you use benzene in your daily life in any way? Benzene. I mean, it seems just like an organic molecule. Do you ever encounter that in your daily life? And the answer is yes. It's like 20% of gasoline. So when you're pumping gasoline, if you ever pump gasoline, you know, if you inhale gasoline, you're getting a small dose of this. Is that enough to give you cancer? Probably not. You know, it's repeat exposure over long periods of time that causes cancer. Working in the laboratory, we would use benzene like in a fume hood so that the vapors get sucked up to the fume hood, right? But is there a simple replacement for benzene that maybe is not toxic, that might have the same kind of properties and, you know, or aromatic solvent? The answer is yes, and that's toluene. So toluene, this is benzene. We have benzene, we have toluene. Well, toluene is used as a sort of a replacement for benzene, and it has less of a carcinogenic effect. And it's really cool because if this does encounter P450 in the liver, cytochrome P450, it also oxidizes toluene, but in a way that's non-toxic. So it oxidizes it to benzoic acid, the carboxylic acid, and that's safely excreted. So that's a very nice, easy polar molecule that can be excreted by your kidneys. So that's the difference between benzene and toluene. Okay, cool. Okay, continuing on the theme of these toxic substances, which I think is interesting to know about because some of these molecules you encounter in your day-to-day life, and but another class of molecules are an interesting example of this are called nitrosamines. Nitrosamines. So nitrosamines have a specific chemical structure. An example of a nitrosamine is it's connected to an amine. It looks like this, N double bond O, connected to nitrogen. You have two methyls on it. Now these are actually found in some meats, overcooked meats. Overcooked meats, some overcooked bacon, for example. So these are actually found in common foods. This molecule is not toxic itself. Just like benzene wasn't toxic by itself, or benzopyrene. Because this is not electrophilic, but it's activated in a way that creates an electrophile. An electrophile causes cancer. So this is actually what we call a we talked about prodrugs. What's a prodrug? A prodrug is something that is not a drug, but it gets activated and becomes a drug. Well, this is a procarcinogen. A procarcinogen. So it's going to be activated, and then it becomes carcinogenic. Okay? All right, so it'll be activated to become a carcinogen. And how does that happen? Oxidized through P450 usually. P450. Where does it get oxidized? In this molecule, it's actually in a weird spot. It gets on the carbon, the methyl. The neighboring carbon down there gets hydroxylated. Well, that doesn't look that electrophilic, right? It's not. If anything, alcohol is a nucleophile, right? But the thing is that this breaks off now. Actually, I'm sorry. Okay, so the hydroxy group kicks in. The hydroxy group kicks in, shown in red. And what actually happens is these electrons break off and go there, and this goes up onto the oxygen. So what does that give you? So now carbon is connected to nitrogen. You have a double bond, and you have an N. You have an oxygen. We're assuming the oxygen got a proton from somewhere, maybe water or something. You have that. Well, that still doesn't look that weird either. But now something kind of weird happens where this lone pair on nitrogen, so that lone pair on nitrogen will actually kick up and kick this off as a leaving group. And the OH probably gets a proton or something. So usually OH isn't a good leaving group, but somehow I got a proton. And now we made a really super toxic substance. So now what do we have is CH3 and triple bond N. Okay, CH3 and triple bond N. You have a positive charge on nitrogen. Positive charge on nitrogen. This is kind of like diazomethane. I'll just write, it's diazo. I'll show diazomethane in a second. But this is, the diazomethane has a loss of a proton. So this is very similar to a structure called diazomethane. Diazomethane is also a supercarcinogen. We'll see that in a second, so hang on to diazomethane. But what happens when you have DNA around? DNA, say your DNA, well, you have a CH3 with an incredible leaving group on it. N triple bond N is an incredible leaving group on it. It's nitrogen, right? What's the DNA going to do? It sees that methyl. What's it going to do to that methyl with the insanest leaving group in the world? It's going to attack it and kick off nitrogen, right? It just attacked it and kicked off nitrogen. What does that give you now? Now you've methylated your DNA, just like before, right? And of course N2. So the gas goes away, and you have the same kind of issue, and this can cause mutagenesis and cancer. Okay, and again, the link between mutagenesis and cancer is not always easy to prove. It's difficult studying the body and just thinking, oh, you mutated your DNA, does that give you cancer? Well, it can with a repeat exposure and long-term effects. If you have a little bit of this happen, and maybe from bacon and overcooked meats, that's not necessarily going to give you cancer, but it can be a contributing factor over many years or decades. So, all right. This is actually studied in a paper that's pretty easy to read. Toxicology. It's a journal. Sorry, toxicology research. Toxicology research, 2018. So it's a pretty recent paper. Volume 34, issue 4, page 371. So this talks about this a bit. Let's see, what else? You can, there's a lot of research and kind of almost like internet discussion, but backed up by scientific research. If you Google, for example, nitrosamine carcinogen, nitrosamine you can see some of the extent of this. I mean, this is a peer-reviewed paper that kind of goes through the controversy of nitrosamines and the carcinogenesis of them. Okay, so what's the overall thing? Is what we started with the nitrosamine, we hydroxylated it with P450, kick off twice, and make diazomethane. Essentially, I'll show diazomethane. It's a tiny bit different. It's essentially this minus a proton. And that's also a pretty well-established carcinogen. Okay? So let's show diazomethane. And this actually is a little bit of a synthetic chemistry thing. So let's talk about diazomethane very briefly. What is diazomethane? So diazomethane is used actually as a chemical reaction. Cool reaction to make esters. Like you need to make a methyl ester. Makes methyl esters. It makes methyl esters. Okay, so what's the reaction and how does it work? I have a carboxylic acid, and I react it with this stuff called diazomethane. And what I'm going to draw it as, I'm going to draw it as that structure. So it's CH2, double bond N, double bond N. CH2, double bond N, double bond N. It has two resonance forms, but this is diazomethane. And what happens, it basically converts a carboxylic acid to a methyl ester. How does it do it? How does it do it? Well, mechanistically, it's actually pretty easy. The big thing is you want to draw a resonance structure of it. Draw a resonance structure. What are the charges of everything? Carbon is neutral. Carbon's neutral. Then we have the middle nitrogen's positive. What about the right side nitrogen? I mean, what's the charge of it? Because you got two lone pairs, and it's the rule was valence minus dots minus dashes. So 5 minus dots minus dashes is 5 minus 6. 5 minus 1, 2, 3, 4, 5, 6. 5 minus 6 is negative 1. So it's negative, right? So it's neutral. The overall molecule is neutral. Carbon's neutral, nitrogen's positive, other nitrogen's negative. Anyway, so you can do a resonance structure where you kick in and kick all the way over the carbon. And what does that give you? you get that. What are the charges now? Something's negative, and something else is negative, and something else is positive. The middle one's still positive because it's nitrogen, there's 4 things on it. Now you have a negatively charged carbon, okay? And this is where this is actually a base, and it takes a proton off. So in the mechanism, CH2 grabs a proton, and that's really easy. And you have O- now. You have a carboxylate. You went from a carboxylic acid to a carboxylate. Okay? And when I said earlier, like, you know, I showed this structure earlier when I showed the nitrosamine metabolism. What I showed is this. I said it's kind of like diazomethane. Well, that's what I mean is okay, so what I was showing was that this was kind of like diazomethane, right? And that, you know, it's diazomethane, but with an extra proton on it. So diazomethane is this stuff. And when diazomethane grabs a proton, it makes this. This is the super electrophile. So super electrophilic thing. Super electrophilic thing, all right? And it's a super electrophile, just like now, rather than using DNA or something, we're doing this in the chemical reaction. So this just attacks, kicks off the N2, and you get your methyl ester. Okay? So that's pretty cool. And so as a chemical reaction, it's amazing because it very, very cleanly gives you a methyl ester. If you need an ester, you make an ester. This is one of those reactions that we say it's easy enough for a biologist to do. Because you really just, you mix these 2 things together and you get the product. And what's the byproduct? The byproduct is what? It's N2, which is a great byproduct to have in a chemical reaction. Anyway, so that's the relationship of kind of diazomethane to the carcinogens, nitrosamines, okay? All right. Okay, let's see what else. So we talked about nitrosamines and diazomethane, and how you know nitrosamines kind of create diazomethane in your body, which is really bad for your DNA because it methylates your DNA. And then diazomethane is kind of a synthetically useful reaction that converts carboxylic acids to methyl esters. Okay, just another little topic in toxicology, sodium nitrite. Sodium nitrite. Sodium nitrite, so this is actually a very controversial thing. It's not an organic molecule, it's a very simple inorganic molecule. It's found in foods. It's found in a lot of cured meats. Cured meats. Cured meats are like things like it's almost like a preservative, or like you might have like pepper roasted turkey breast, or I don't know, things like that. If you eat meat, smoked turkey, things like that. And a lot of it's used as a preservative in a lot of kind of like deli meat type things. Often though, like if you would buy turkey breast like at a deli, it would not have this. But if you have it like the kind of processed equivalent, and you look in the package, you might see sodium nitrite. And anyway, there is a little bit of controversy behind sodium nitrite, and I'll show that. I'm not going to take a position on this, although some people think that sodium nitrite is actually carcinogenic, or it could be with with long-term exposure. So what is sodium nitrite, and what could it potentially do to molecules? Na+, O-, Okay, this is sodium nitrite. Looks like an innocent little molecule, inorganic molecule. Let's just assume it gets protonated twice on the oxygen. So protonate the oxygen twice. What does that do? So do that twice. You get O. You're basically a leaving group on oxygen now. Sorry, leaving group on nitrogen. Okay, and then this can kick this off and make nitronium ion. It makes nitronium ion. I flipped it around too, so I put the nitrogen, this right side oxygen over here, and that becomes left. I just did that too for my mechanism. Now, a lot of meats and foods have amines in them, especially meats, and a lot of fishes and things like that. Fish and meat have amines in them. Well, anyway, guess what happens when an amine sees this? It actually attacks nitrosium. I got this wrong. It's not nitronium, it's nitrosium. Nitrosium ion. Let's do that. Nitrosium ion. Well, what does that give you? That gives you these nitrosamines. So, of course, this metabolizes to diazomethane. And then that is a carcinogen, right? So cancer. Ultimately, mutagenesis and carcinogenesis, okay? Okay, and so is it safe to have sodium nitrite in your meats or foods? It's very commonly found in meats, in deli meats and these kind of smoked turkey type things. It's controversial, right? And there's definitely people in like the meat lobby and the smoked meat lobby, and there's a lot of people that are saying, well, it's totally fine, it's okay. It's hard to prove ultimate links to cancer, and so there's no simple way to just say, oh yeah, this is definitely a carcinogen. Proving something is a carcinogen is a long-term process. Certainly the links to making the nitrosamines and the links from nitrosamines to diazomethane and the links of diazomethane to methylated DNA, that is pretty easy to establish. But cancer is another story. So again, I'm not going to take a position on this, and you can definitely read about this and make your own position. But it is an interesting story, definitely. If you do research this, you'll see that there are lobbying efforts from companies that are trying to say that nitrites are totally safe in foods. Okay? Yes, so just wanted to mention that. All right. Okay, so I think we're done with the toxicology section. I want to move a little bit on to drug names and nomenclature before going into a couple more details about pharmacodynamics, right? How drugs interact with your body and like dose response. That'll be probably next lecture, but I'm going to start the next section real quick. Okay, so next section is on drug naming, drug names and nomenclature. And I also should mention that I think I mentioned this before, but what I'm following right now is actually a written document on the iLearn site called Basic Pharmacology. So you can read along with this, and you should be doing that. Check out the PDF file and also some of the figures and things like that, which we'll get to some of those figures next time in the Basic Pharmacology section. But in that file right now, there's a section called Drug Names and Nomenclature, and we're going to briefly talk about that. So let's just give one example, and I'll give another example next time. All right, aspirin. This is typically known as aspirin. But there's a bunch of other names for aspirin. So what are the different kinds of names and related to drugs? So what are the names? There's one's called the chemical name. This is often also called IUPAC. So IUPAC, the IUPAC name of this is not aspirin, it's called 2-acetoxybenzoic acid. Acetoxybenzoic acid, okay? The trivial name is also called a common name. Is based on some sort of historical naming of the molecule. So this is often historical. So it's not necessarily IUPAC. And in this case, oh, sorry, I messed up my structure. Let's fix the structure real quick. Okay, sorry about that. Yeah, here we go. There's the structure. I forgot to put the acetoxy group on the molecule. Forgot to put the acetoxy on there. Okay, so now we have the correct structure of aspirin. The chemical name is 2-acetoxybenzoic acid. And now you see the acetoxy group there on the bottom. Okay, so we got that. What is the trivial name or common name? And it's often based on historical precedent for these molecules. And so, well, if we look at the kind of the core structure, which is what I drew earlier, it's like that with the oxygen like that. Then that molecule is called salicylic acid. So that thing is called salicylic acid. I'll draw it down here. Salicylic acid. Salicylic acid. It's not. Don't say salicylic. It is cyclic, but it's not. The name of this molecule is salicylic. SALICYLIC. Salicylic acid. Okay. So the trivial name for aspirin is based on the trivial name of the root, salicylic acid. So it's salicylic acid with something on it. And the trivial name for this is acetyl salicylic acid. So that's the acetyl group, right? So the trivial name for this is acetyl salicylic acid, okay? So those are two different names for aspirin. And then we also have the generic name. Generic name is more of a pharmaceutical name, and that's non-proprietary. So this is like a commonly used name that does not have to do with a company. So it's non-proprietary. It's non-proprietary. And what's the generic name for this molecule that might be used in the clinic or pharmacology that's not related to a business name? And that's aspirin. So the generic name is aspirin. Okay, so we have the IUPAC name, or we call it the chemical name. We have the trivial name, which is based on common naming in organic chemistry, common naming. And the generic name. So the generic name of this molecule is aspirin. Okay? And then are there any other naming methods for drugs? And the answer is yes. We also have trade names. So these are proprietary. So the proprietary name of this, and there's multiple, and it has to deal with companies that actually sell it. And one example is bufferin. Bufferin. So bufferin is a specific brand of buffered aspirin because it's carboxylic acid, it has some buffers and inorganic salts that make it less problematic on your stomach. Okay, so this is an example of using aspirin and how we might name aspirin. There's multiple ways to name it. You see all these names in pharmacology and people talk about drugs. Okay, I'm going to show one last example of chemical name versus trivial name or common name. Is, we'll say benzene, this molecule. So this is not a drug. We have a couple names for that molecule, right? But this shows the difference between like a chemical name or IUPAC versus a common name, and I just wanted to mention it. So what's the IUPAC name of this? It's a methyl on a benzene, so you call it methylbenzene, right? Methylbenzene. Methylbenzene. That would be kind of like a systematic named thing. So we start with the benzene, we have a methyl on it, it's called methylbenzene. And then what's the common name, which is the name that everybody in the universe uses? That's toluene, right? Methylbenzene and toluene. That's just another example of common naming versus like a formal IUPAC chemical naming system. So we'll have a couple more examples like that, and then I'll keep going into more pharmacology. Hope the lecture was clear. Still getting better at this, and yeah, I'm going to try to give you guys 2 lectures a week, just like you got normally, but there won't necessarily be, it won't necessarily be Tuesday and Thursday morning. You might see them on a Wednesday and Friday or something like that. All right, and we'll have some new homework eventually as we're getting established. All right, have a great weekend.